Welcome back. Now that we have some familiarity with the binary system, let's try to work out how to do addition using circuitry. So remember, computers speak in zeros and ones, as I said last week, and to represent numbers, computers use the binary system. This means that if we want to add two binary numbers together, we have to develop a circuit to do this. So let's think about an addition circuit. Conceptually, I can represent it by some black box for the time being, well, blue box, with the symbol plus to denote that we're doing addition. And this should take two inputs, so two numbers should be fed into this addition machine, and it spits out one output. These inputs can be multiple digits long. For instance, maybe this is a 5-bit addition circuit, in which case it takes in one 5-digit number and another 5-digit number and spits out their sum. So in this case, I'm doing 22 plus 21 is equal to 43 again. So something, first of all, peculiar happens, where you're adding two 5-digit numbers, but there's a possibility that you might get a 6-digit number. And in practice, this happens, as you can see in this example. But this is kind of a complicated circuit. I mean, on this side, you have 10 inputs into the circuit, and on this side, you have 6 outputs. So that means there are 10 wires going into this circuit, and there are 6 wires coming out. And there's a bunch of logic gates scattered through the middle of this, which take all the different inputs, do a bunch of complicated things with them, and spit out 6 different wires. So this is a bit complicated to build just from scratch. So let's try to simplify the problem. Instead of looking at 5-digit numbers, we can look at 1-digit numbers to start with. This leads to the notion of a 1-bit adder. Well, a 1-bit adder is something that takes two 1-digit binary numbers and adds them together. So for instance, if I do 0 plus 0, I should get 0. If I do 0 plus 1, I should get 1. If I do 1 plus 0, I should get 1. But then something funny happens, where if I do 1 plus 1, I get 1, 0. So if you look at these first examples, the first 3 examples, you might naively think that you can just take two inputs and spit out one output. But the problem arises when you look at this 4th example, where I take two inputs, add them together, and I get 2 outputs. So really, a 1-bit adder is a circuit that should take 2 inputs and give you 2 outputs. And the way to make this work with the previous 3 examples is just to add a 0 in the second column. We have nomenclature for these two different place values. This output is called the sum bit, and this output is called the carry bit. Why are they called these things? Well, if you remember the addition problem that we did before, if you take 1 and 1 and add them together vertically, then you get a 0 on the bottom and you have to carry the 1. So 0 is sort of the sum, and then 1 is the temporary carry bit that you put in the next column when you continue your addition problem. So really, in most of the examples, these first 3 examples, the carry bit will be 0. But in this exceptional case, the carry bit will be 1, and we do need to keep track of it in order to get the correct answer. Okay, so we have 2 inputs into a circuit, and we have 2 outputs. And we know what they are, so we can look at the truth table. So the truth table is exactly as written over here, just copied into this nice form, where A and B are the inputs, and the sum bit and the carry bit are the 2 outputs. So as shown on this side, for instance, if I take 1 and I add it to 1, then the sum should be 0 and the carry bit should be 1. But this is kind of nice. If we now want to take this truth table and turn it into a circuit, we're in a good position to do so because the sum column looks exactly like an exclusive OR, and the carry column looks exactly like an AND. So the sum should be really just the exclusive OR of A and B together, and C should be the AND of A and B together. So let's do this. So here's the schematic diagram of the circuit. These are my 2 switches, which I can change to 0s and 1s. Here's an exclusive OR gate. Here's an AND gate. And both of my inputs are being fed into both of these gates. The exclusive OR gives you the sum. The carry gives you the AND gives you the carry. Great. Now we know how to do a 1-bit adder. So let's do a 2-bit adder. This is the sort of next hardest problem. Now I want to take two 2-digit binary numbers, add them together, and get a new binary number. So 2-bit addition can be really broken down into 1-bit addition. If you write this down on pen and paper, first you add the digits in the ones place, then you add the digits in the twos place. So the naive thing to do is to try to use two 1-bit adders. We already know how to build 1-bit adders because we just did that in the previous slide. So let's try to take two of them and put them together. So here are my two 1-bit adders. I'll add the input wires. And for the purposes of this illustration, why don't I look into specific examples? So in this example, 1, 1, which is the number 3, is being added to 0, 1, which is the number 1. And the result should be 4, which in binary is represented as 1, 0, 0. So this top adder should be for the ones place, let's say, and this bottom adder should be for the twos place. This means that I take the numbers in the ones place, which in this case are 1 and 1, and I stick them into this first circuit. Then I take the numbers for the two place, which are 1 and 0, and I stick them into the second circuit. Okay, let's run the circuits. In the first circuit, I get a sum of 0, and I get a carry of 1, because I'm adding 1 to itself. In the second circuit, I get a sum of 1 and a carry of 0, because I'm adding 1 to 0. Now, if you look at this output, clearly something's going wrong, right? The problem is that I have the solution over here, which is supposed to be 1, 0, 0. But if you read off this solution, it's not clear why this should represent the sum of the two numbers that I put in. And the problem is that there's a carry bit coming out of this first adder. And this carry bit is supposed to go into the second adder. Right? When you do an addition problem, if I add 1 and 1 together in one column, and then I drop a 0 down below, the carry bit goes into the second addition. So this 1 should really be factored in to this second addition. So what that means is that this circuit is not really enough. We need a modified 1-bit adder which accounts for this carry bit. So let's think about this modified 1-bit adder. We can summarize the situation in the following truth table. We have an input carry bit, which comes from the previous addition problem, 1-bit addition problem. And we have our two inputs for this place. And then we get a sum, and we get a output carry bit. So really what we're doing here is we're taking C in, and then we're adding it to A, and then we're adding that to B. And then we get a sum, and we get a carry. So if everything is 0, we should get 0. If exactly one of these is 1, so the second case, the third case, and the fifth case, then the sum bit should give a 1, and the carry bit should be a 0. On the other hand, if two of these numbers are 1, like in this fourth case, or the sixth case, or the seventh case, then the sum is 0 because it's 1 plus 1, but then we've carried a 1. The final case, and the only exceptional case, is when 1 gets inputted as a carry, and 1 also gets inputted as both of the inputs. Then I'm really doing 1 plus 1 plus 1. So the sum on the bottom should be a 1, and I'm also carrying a 1. Which makes sense because 1 plus 1 plus 1 is 3, and 1, 1 in binary is 3. So to create a correct 2-bit adder, we need a circuit that realizes this truth table. Now, since you have seen last week how to construct circuits, and since you have some experience playing around with these different logic gates, I would like to leave this part as an exercise. I think this is a nice way to play around with these digital circuits and try to construct something which computes the sum and the carry output from these three inputs, and more importantly, try to do it in the most efficient way possible. So I'll give you two hints, one of which is that you can try to use the switch technique from last week. If you remember what the switch technique was, it's the ability to use different circuits depending on the value of a certain bit. So in this case, if the carry bit is 0, we want to do one particular thing. But if the carry bit is 1, then we want to do a completely different thing. And so this could sort of fall into the framework of the switch technique we had last week. On the other hand, if you use this technique, which I do suggest that you try first, you might get something very complicated, and it's worth trying to come up with something simpler. But if you want to do this exercise and you're stuck on where to begin, I would suggest starting with the switch technique. So let's suppose that we've built one of these modified 1-bit adders. Let's suppose that you've done this exercise. Then let's look at this problem again. 1, 1 plus 0, 1 is 1, 0, 0. Again, we put 1, 1, which come from the 1's place, in this first circuit. And we put 1, 0, which come from the 2's place, in the second circuit. But now we have an input carry bit, and we have an output carry bit, which feeds into the input carry bit of the second circuit, which then spits out an output carry bit. For the first adder, there's no carry, because I'm just starting the problem off. So this wire should be coming from a constant source, 0. Or, if you want to make this a bit simpler, you could just make this first 1's place circuit the 1-bit adder that we defined first before the modified one. It doesn't matter. But if I put 1, 1 through this circuit, I get a sum of 0, and I get a carry of 1. So then I feed this 1 into the second adder, along with the inputs 1 and 0. And now the problem looks like 1 plus 1 plus 0. So if you look at the truth table from the previous slide, 1 plus 1 plus 0 should give me a sum of 0 and an output carry of 1. So the sum is 0 and the output carry is 1. And if you think about the correct way to read off the result, this carry bit should come first. So I get a 1, and then I get this sum, which is 0, and I get this sum, which is 0. So the solution is 1, 0, 0, or in other words, the base 2 equivalent of 4. So here is a complete 2-bit adder. As promised, it takes 2 inputs, both of which are 2 bits, and it spits out 3 outputs. Because if you add two 2-digit numbers together, you might get a 3-digit number, depending on which numbers you chose. Okay, so this is an explanation of how you make a 2-bit addition circuit. In the exercises, there's going to be a lot more on this topic. So in particular, you need to fill in the modified 1-bit adder that I didn't actually give you a recipe to construct. And then part of the exercise is to figure out how to do an n-bit adder, where n is now any positive integer. So instead of doing a 2-bit adder, you might want to do a 3-bit adder, or a 4, or 5, or 6, or 7, or 8. And the exercises will ask you how to do this, amongst other things.